do that. All right, so we're going to title this lesson Three Forms of Linear Equations. Of course, the first one, we're just going to sort of review because we already talked about this in our last lesson, right? But it was the connection of our slope-intercept form. So that was our y equals mx plus b format. We talked about how that is directly created or connected to, our explicit formula or rule, however you want to think of that, from our arithmetic sequences, right? Which was, any term number can be found by the common difference times that term number plus the 0th term. And so just being able to connect these two here together, knowing that they are the same thing, just two different angles, right? So we're standing at one side of the room looking at the statue this way, and now we started standing on the other side of the room and we're looking at the same statue coming back. Now, just to kind of summarize this one just a little bit for us. So this format, this slope-intercept explicit formula, is usually used with a stated / easy to find slope or common difference and a clear y-intercept / 0th term. Again, we can do a little underlining here, right? Like slope and common difference, we now know are the same thing. And our y-intercept and our 0th term are the same thing. So we're connecting those two front views, the Algebra 2 view, the Algebra 2 language, the Algebra 1 language. Okay, so here's where we're going to paste in our first of our cutouts. And so let me show you which one we're going to do. So we're going to grab this one right here that has the 2 points at 2, -3, and 8, 0. You're going to take yours and you're going to paste it in, and I'll show you where we're just going to put it right below here. Like that. Okay? So you're going to paste that cutout right there onto your notes. So just grab your glue stick and glue that right down onto your notes there. I'll give you a minute to do that. If it's stuck, you can just grab another one. So this would be the example of, a stated or easy to find slope or common difference and a very clear y-intercept. And so here's the idea. I think I thought about this the other day. I should have brought my tools in because, again, this is what we're talking about. We're talking about 3 different tools to use at different times and knowing which one is the best one to use. So, like, for example, slope-intercept form or explicit form really works well when you have a very clearly, easily stated slope or y-intercept. Like, for example, that point right there. That point's pretty obvious, right? What's the address for that point? Right, so that's 0, -4, right? And that's really clearly a y-intercept for us, right? So then we can pretty easily calculate our change in y and our change in x, right? Like if I go here like this and here like that, what would be my change in y and change in x? Let's write that in there for that one right there. The change in y is what? Yeah, it's up 1, right? So the change in y is up 1, and what's the change in x? 2. Right, 2, so positive 2, right? Okay, good. All right, so then that would give me a slope or a common difference of 1 over 2, right? But it should be, if it's the same line, then it should be like wherever we check a point for sure, like this one and this one right here, right? What would that one be? What would be the change in y for this one? Yeah, it'd be plus 3 for a change in y, and then 1, 2, 3, 4, 5, plus 6, right? Which still works out to 1 over 2, right? And again, that's what we said the other day. We want to use our most simplified common difference, right? That will help us get that value that we want for that d. And so then we can just jump right to writing our equation. If we can see the y-intercept, and we can easily find or have stated the slope or common difference, then in our explicit formula language, we could say the equation of this line would be a sub n what? You write it out. What would it be in Algebra 2 language? Look much different than Algebra 1 language, just instead of using x's and y's, I'm using a sub n and n, right? But it's basically the same idea. And I mean, if, just for sake of looking at it from that other angle, we could say this is the same thing as y equals 1/2 x minus 4, right? This is just looking at the statue from the left, looking at the statue from the right, that's all. But now you've got more language to put with it, right? It's now not just slope-intercept form, it's also explicit formula of an arithmetic sequence. Right? If I had said explicit formula to an arithmetic sequence before coming in here, some of you may or may not have known what that meant, but now you can connect those two together. Okay? Good. That's easy, right? Simple review. Okay. Let's talk about our second tool then that we're going to look at. All right, so our second tool we're going to look at is called standard form. Our second tool is called standard form. Now, there are some, I want to call them rules, guidelines, fairly common patterns that you'll observe in regard to standard form. They probably should be followed, but they're not always going to be. But I'm going to give you them so that you get some basic ideas of what we're talking about. So when we're talking about standard form, your x and your y, which is going to be your input and your output as we continue to kind of move along in our function language. We're not there yet, but that's going to be on the left side of the equation. And your constants, means your non-variable terms, are going to be on the right side of your equation. And right, left, they could flip-flop, but the idea is that the variable terms are on one side and the constants are on the other side. Now, we also tend to see that A, which we'll talk about in a second, is positive. And we'll see that A and B are integers, which means that we don't have any fractions or decimals. And then lastly, there is usually no GCF for A, B, or C. Now you're wondering where I'm getting these letters from. Our standard form is usually written like this. And this is something that you should have seen in your kind of Algebra 1 perspective. This would be like middle of the whiteboard over there, view of the statue. It's your standard form. Okay, now, standard form is usually used to relate two unique items. So standard form is usually used to relate two unique items. Okay, so let's get our second paste up here. So the second paste up that we're going to do is this one that says Mora has 2 hours. So we're going to grab this one. And then we're going to paste that one right down in here where we're relating these two unique items. So let's paste up Mora and her chores. Standard form and relating two unique items. So Mora has 2 hours on a Saturday to do chores. It takes her 20 minutes to dust a room, and it takes her 15 minutes to fold a load of laundry. Two unique items. Let's highlight them. Dust a room and fold a load of laundry. These are our two items. Oh, sorry. These are our two items here. Dust a room, fold a load of laundry. So this is what we're going to use standard form to connect these two items, right? Now, we've got some values to this, all right? You can see here, though, in the question, it tells us right here that we're going to give all the possible of rooms she can dust, X, and then all the loads of laundry she can fold, Y. So we're going to define our variables here. X is the number of rooms dusted, and Y is going to be the number of loads, we'll just say loads folded. Okay, we're going to take this 2 hours here, and we're going to convert that into minutes. How many minutes is 2 hours? 120 minutes, right? Okay. Because we're working in Mora's time frame is in minutes, so we'll work in minutes. What I want you to do is, I want you to write the literal standard form equation, like as it's stated right here in the problem, not a simplified version of it. I want you to write it as it's stated in the problem. What would you write right here? We're going to do two of them, one here and one here. So in the top one, what would you write for a standard form equation that would tie together these two items? Give it a try. If you don't get it, you don't get it. Give it a shot. But it's worth a shot. Give it a try. Put that. Right? That's the literal, as it's stated literally in the problem, 20 minutes per one load, or 20 minutes per one room dusted, and 15 minutes per load folded, right? And that breaks us down into this 120. However, we can simplify this, can't we? Right? Because there's a GCF. What's the GCF here? What number can we divide all three of those terms, 20, 15, and 120 by? We can divide by 5. Okay, so let's write the simplified version of this, which is going to be divide by 5, so it's going to be 4x plus what? 3y is equal to? Y'all have calculators. What is it? 24. Okay, so this would be the literal standard form right out of the problem. This would be the simplified standard form. In fact, we can kind of write that down. We can say literal, right? That comes right out of the problem, and then simplified. And one of the things that we oftentimes do with this relating of these two items together is we ask questions like, let's ask this question. So if she did no laundry, how many rooms did she dust? 6 rooms? Is that legit? Wait, if she did no laundry, if she folded no laundry, she did 6 rooms, right? Yeah. Okay. Okay, good. So, and we could say, so 6 rooms. We could actually relate that like a ordered pair, right? We could say, so she can do 6 rooms dusted when she does 0 folding of laundry. That's a kind of a math shorthand way of writing that. Yeah. Okay. How about if she did no dusting? Why don't you fill in what you think would go here based on what we just did there? Go ahead, write it in. Put 8 loads folded, no dusting. She can fold 8 loads of laundry, right? So we have the extremes of these situations, right? We can look at it and we can say no rooms dusted, how much laundry can she fold? No laundry folded, how many rooms can she dust, right? And then we can take that information and we can kind of relay that into a visual image, which is something that we're going to do a lot of in this class. So let's do this. We're just going to sort of sketch in a line here. We're going to kind of sketch in a line here like this. Right, and our X is what? What is our X in terms of the story? Okay, so dusting, right? So we got dusting down here, so then we got folding over here, right? And so if she does no laundry, we know she can dust 6 rooms. So no laundry, that means we wouldn't go up this at all. So we'd come over here, and we'd put a point right here, and that would be our 6, 0, right? And then if she did no dusting and all laundry, then we could come up here and we could put a point up here, and that would be 8. Oops, that'd be 0, 8. And then we could connect those, right? And then we could talk about all the combinations in between. I mean, is it possible to dust 1/4 of a room? Sure, why not, right? I mean, you could do part of the dusting, right? You dust 1/4 of the room, right? And then you have some left over after that, right? Oh, 3:30. Yeah, I was going to say, not 3 o'clock, right? Okay. Yeah, so, I mean, it's possible for us to have a continuous graph here because we could have parts of that, right? Doesn't really make sense to extend it, but again, we could think of it like that. So this is what our standard form does. It usually takes these 2 unique items and compares them together. And so if we have a situation like that, this would be the perspective that we would want to use. Good? Everybody okay? Standard form. All right, moving on. So let's talk about the one that you may or may not have gotten a look at in Algebra 1. It kind of just depends on who taught you Algebra 1 and what your curriculum was. Oh, if you had Dr. Newsom, you got this then. All right, let's talk about point slope form. Okay, so point slope form looks like this. It's got a pattern of y minus y sub 1 is equal to m times x minus x sub 1, like that. I don't think we did point slope in geometry. No, I don't think so. Now, your m, of course, is still your slope. This x, without the sub number on it, is the input to your function. This y, without the sub number on it, is the output to your function. So then the question becomes, what is this x and what is this y? And that is the point of point slope form. So let's just kind of make a note here as we kind of talk about this a little bit. So this is usually used, again, with a stated or easy to find slope or common difference, right? And any other point. So previously, right, and we're going to say any other point slash term. That would include the, term number and sequence value, right? We'll do some underlining again just to make sure we keep things consistent, right? Our slope and common difference are the same, and any other point and term are the same. So what makes this different than our slope-intercept form is we don't have a clear y-intercept, right? And that's where this is particularly helpful. So we'll just make a note of that. This format is helpful when your y-intercept, also known as your a sub 0, right? I can probably write that clearer. Your 0th term, your a sub 0, is not an integer. And I'm going to say etc. because You might have a graph where your line is just way off and you don't even have a y-intercept in your picture. And so then it's like, it's not obvious. It's not clear what the y-intercept is or what the 0th term is. And so maybe in that case, you just want to jump to using point slope form. And that's where you would use this one. Okay? All right, so let's go grab our third paste up here. So our third paste up is going to be this one with the graph with the little 3, 8 on it. So let's grab that one. That one is going to go. Thanks. Hang on one second. Okay, thanks. All right, so we're just going to paste this one right in here.
To be honest with you, I would rather you stick around and do what
We're doing here first and then go, and then if there's a problem with that, I can send an email because I don't want you to miss something, especially towards the end of the lesson. Okay, well, we'll see where we're at. Okay, so we're pasting this in here. I'm gonna flatten mine down. Okay, and then we'll take some notes in just a second when you're all pasted up and ready to go. Okay, ready? Paste it up? Okay, let's take a look. So let's start with this right here. Clearly, we don't have a very easy to define y-intercept at this point right here because it's obviously somewhere between 7 and 8, but we don't really know fractionally how to break that down. We could guess, but we don't know exactly what it is. So we don't have a clear y-intercept, so this might be a good candidate for point slope form, right? But we do have another point on that line right here, which is pretty clear to see. What's the address for that point? Okay, yeah, so that point is 7, 9. And that will allow us to fairly easily determine our common difference of our slope, right? So we start and we go change here and change here. And what is our change in y in that case? Okay, up 1, right? And what is our change in x? 4, yeah, 4. Okay, all right. Okay, so we got a fraction. We got a fractional slope here, right? Not like a whole number that simplifies down. Okay. All right. Well, let's do this. Let's use this point right here, and we'll use this space right here on our paper. So why don't you write what you think the point slope version of a equation for this line would be? Just write it right here, and the point we'll use will be this one right here. Go ahead, give it a try. Again, if you don't get it, no big deal, but give it a shot. With that. Yeah? Okay, now, the question that always arises here is, well, wait a second. That's a positive 3 and a positive 8, Mr. Vargas. Why is it negative in the equation? And that's a legit question to ask because really, if you go back to the actual slope-intercept or point-slope format here, you'll notice that the format itself is y minus and x minus, right? And then it's the point just goes in that box right here that you drop it in. So really, the format itself contains the minus, and the point just drops right into that box. Why is that important? Well, that's important because you're going to see point-slope equations that might say y plus 8 over here. And if it says y plus 8, what's important is you understand that that comes from y minus negative 8, and that the actual value inside this box is a negative 8 at that point. Okay? And that's going to arise a lot for us in this class. All right? So this idea of the format containing this minus in it is going to be super important. Okay? And again, like I said, you're going to see this a lot as we kind of move through. All right? Well, let's do this. Let's do a little, just for the fun of it, let's do a little divider here like that. because I chose to use the 3-8 point, right? But we found our common difference using the 7-9 point, right? Which means it's on the line. We wouldn't be able to find the common difference if it wasn't on the line. So why don't you write the point slope of the equation using the 7-9 point over here? Okay, let's see what you can do. Go for it. Could have written that. Yeah? Good? But how do we have one line and two different equations? That would be like having one arithmetic sequence with two common differences, or one arithmetic sequence and another one, but then it's the same relationship, but yet it's not, or is it? Well, let's do this. Let's do this. Let's solve this equation on the left here for y. Let's solve it for y. Let's get y all by itself, and let's simplify all the math we can do. So, like, for example, we could take this -9 right here, and we could move it to the other side, right? And we could, while we're doing that, we could do some distribution here, like that. And so let's kind of clean things up and move things around a little bit. So what would the next step of the equation look like if I was going to move that 9 over and do some distribution? Why don't you write it down? What do you think it would look like? Go ahead, give it a try. How about this? Does that make sense? Right, distributed the 1/4, right? Move the 9 over. Just got to simplify. Are there any like terms I can combine together? Yeah, those are both constants, huh? Yeah, so we could put a 7/4 in. They had a weird. That's like a fraction in a whole number. I could turn the 9 into a fourths number, couldn't I? Yeah. What would that be? What would that be as a fourths number? Okay, 36 fourths, right? Is everybody got what I did there? Yeah. Okay. All right. So then, y is equal to 1/4 x. What do you got? 29 fourths plus, yeah, it's plus, right? Plus 29 fourths. That might be easier to understand as a mixed number since we're on a graph, right? Like, let's get the whole number parts and then we can see that, like, so what's that as a whole number? Well, let's just stay in fraction. We're working in fractions. Let's just stay in fractions. So plus 7 and then, right, 4 times 7 is 28. There's one more left over, right? So the remainder goes up top, 1/4. That's also going to come into play for us later on. Remember with your fractions, right? The remainder of the division problem is actually the numerator of the leftover amount. Okay, all right. Well, let's do the same thing over here with this one then. Let's solve this one for y. So the first thing we do is we move the 8 over and do some distribution, right? Yeah, did you get this? Okay, good. All right. 3. We put the -3/4 and the 8 together, huh? Well, we don't really need to put that into a fourths number, do we? I mean, we could take 75 cents off of $8, right? What's 75 cents off of $8? 7, oh yeah, 7 1/4, huh? Oh, so it's y equals 1/4 x plus 7 1/4. Now, those two are actually the same equation, aren't they? Okay. Well, they would have to be the same equation. Same line, same equation. So when you're in point slope form, you can have a lot of different variations of that. 1/2, 3/6, 7/14, 10/20, 25/50, right? But when we simplify it, we get 1/2. It's just like prime factoring a number, right? If I said prime factor 28, one of you might have started with 7 and 4. You could have started with, 2 and 14, right? There's a lot of different math problems we can do. But when we say prime factor, we're all going to end up at the same place. So when we take our point slope forms and we convert them to what now is slope intercept form or explicit form, right? We're going to end up at the same place, okay? And so that's how you affirm that you've got these multiple variations of your equations the same, all right? That's how you would prove that. Right? If I said, show me that those are the same, you would put them both in slope intercept form. Good? Everybody okay? All right. Last thing we're going to talk about for today. So I want to take a minute and I want to do a little foreshadowing. Okay, I want to do a little foreshadowing here. And before we do our foreshadowing, let's go get our last little paste up that we made for the day, which is this graph right here. Let's grab that. Okay, now I'll show you where I want you to put this one. So this one we're going to kind of paste over here a little bit to the side, like right about there. Okay, so get that one glued up. There was a little printing error that I need you to fix. So right here, this little +5, we're going to cross out that plus, and we're going to make that -5. That should have been a -5 right there. So right here, this little +5, change that on your paper to -5, a little printing error. Okay, little foreshadowing. Here we go. Let's start with our slope-intercept form. And I'm going to start to do that whole solving thing we were just doing a second ago. So I'm going to move my y sub 1 from the left to the right. So I'm going to start to solve this for y. So now it's going to look like this. Okay, now I'm going to change the letters on you. Oh, sorry, wrong letter. So I'm going to change the letters on you. X minus h plus k. Now, I'm going to tell you this. A, in this case, controls the slope of the line. I'm going to tell you this. H controls a right-left translation. And I'm going to tell you this. K controls an up-down translation. So A, H, and K. What do I mean by translation? Yeah, but different in a specific way. What is a translation? We really actually didn't talk about this in geometry. It's a part that gets left out in our curriculum, but we should. I agree. I think we should. Yeah. Right. Exactly. So it's like moving a shape without changing its size. It's called a rigid transformation. So like, you know, if I were to take this paper was my coordinate grid and then I had this square on here, a left-right translation would be if I slid this left or right, and an up-down translation would be if I slid this up or down. It doesn't change the size of this shape at all. We change that size. That's called a dilation. That's similar figures versus congruent figures, right? Here and here are congruent shapes because of the same size, just different locations, right? So translating is sliding up and down and left and right. And if I slide if I slide left and right and up and down at the same time, that's when I start to move diagonal. And so a combination of up and down and left and right movements allows me to move anywhere on a flat two-dimensional plane that I want to, okay? All right, so let's do this. Let's start with this y equals x right up here. And I want you to point a little arrow up here because really what this means is y equals 1 over 1x plus 0. And this right here is called the linear parent function. And again, we're going to get into more of this in detail, right? This is just a little foreshadowing. But this is called the linear parent function. So there's a base line, a parent line, a main line, the line, like the man, okay? All right, and that line starts at a y-intercept of what? 0, and has a slope of what? 1 over 1. So up 1, right 1, up 1, right 1. Or down 1, left 1, down 1, left 1, right? So let's draw that line on our graph. So I start at 0, 0, and I go up 1, right 1, up 1, right 1. I can even go down 1, left 1. I'm going to change my little color here. And we're going to draw that line on our graph. I'm going to flatten my thing so I can work on it here. So we'll go like this. No, that's not what I wanted to do. Okay, so I'm going to go like that. And then I'm going to extend the line in both directions for a little bit. So I got some line to work with here. Okay. Now, you'll see that we have this newly formatted parent function here with our A, our H, and our K. See that? Now our A controls the slope of the line, right? So here's your parent function line. You're looking at it right here, right? Here's your coordinate plane right here. Here's your 0, 0, y-intercept, right? You've got this parent function of this line, right? And I can change the slope of that line, which is going to turn it somehow like this. So however I change the slope, it's going to rotate that line, right? So I can turn that line like this. And then I'm going to take the y-intercept and I'm going to shift it. I'm going to translate that y-intercept point according to my h and my k. So in this particular case, you can see the format following what we talked about with our point slope, right? H is +4, k is -5. So that means I'm going to take my y-intercept that's at 0, 0, and I'm going to go clunk, 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 4 to the right, and then clunk, 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 5 down. So I'm taking my parent function line, I'm shifting it 4 to the right and 5 down, and then I'm going to change the slope to 2 over 3. More like that. Okay? And so I'm taking that starting function and I'm transforming it by changing the slope and changing the location of the anchor point, which in this case is our y-intercept. Okay? So the way that we would do that is we would take, I'll do this one in blue. So we're going to take this y-intercept point here, right? And we're going to go 1, 2, 3, 4, 1, 2, 3, 4, 5. So I translated it. Make that a bit smaller so it doesn't look like an actual point. And then from there, I want to do my new slope of my line, which is 2 over 3, right? So I want my up 2, right 3, 1, 2, and right 1, 2, 3. And I can do that again, or I can go backwards. I can go down 2 and left 1, 2, 3. That, right? And then I can draw my newly transformed line here. Like this. And so I've taken that parent function equation and I've changed the look of it by changing the slope and changing the location of the anchor point, which in the parent function for the linear is the y-intercept point at 0, 0. What's that? Well, yeah, it changes every part of the line. Yeah, I transformed the line. I turned it into a new line. But instead of just thinking it as drawing it from one particular location point, what I've now done is taken the parent function and adjusted the parent function accordingly to the transformations. Okay, let's talk about that for just a second, right? So I want you to think about something. What would this, if I had given you this line here, and I'd said, okay, since it doesn't have a really clear y-intercept, right? If I'd given you this line right here, and I said use this point, what would it look like in point-slope form? What would the equation look like in point-slope form? Well, you'd figure out your slope, right, which is your 2 and your 3, right? And then what would you put here and here? Well, you'd put a 4 here, right? And you'd put a 5 here, right? Because it's 4, yeah, and negative 5, right? So then this would be written y plus 5 over here, which comes from y minus negative 5, which is the point at 4, negative 5, right? But think about that. If we took that plus 5 and we moved it over to the other side, what does it end up as? It ends up as a negative 5. So that shifting to 4, 5 is just relocating the y-intercept to the point that would have been in our point-slope form. See the connection? Okay? And we're going to do this with all different kinds of functions. We're going to take our parent functions, we're going to know what those are, and then we're going to translate them. And so what I'm going to ask you to be able to do is be given an equation like this, describe to me what happened to the parent function. So instead of graphing the line, now I'm going to give you this, and you're going to tell me what happened. You're going to say, well, Mr. Fargas, the parent function, which has a y-intercept of 0, 0 and a slope of 1, was shifted to the right 4 and down 5, and the slope was changed to 2 over 3. You're going to be able to describe that like that, but with a variety of different functions. We're going to do that with square root functions. We're going to do that with exponential functions. We're going to do that with quadratic functions. We're going to do it with all kinds of different functions. And so you're going to have all these parent functions. We're going to be transforming them and changing, but you'll notice this pattern that sort of kind of exists with that. So still foreshadowing. Okay? All right, so just kind of give you a little preview of some things that are coming down the line as we get a little bit further in the class. Okay? All right, that's going to do it for our 3 vantage points at our lines.